Okay, and this is the final step that we wanted to cover today, which is that of CPA security. So we'll give you I'll give you a construction which shows which one can prove. We'll not prove it, but one can prove satisfies CPA's indistinguishability or CPA security. So what is the construction? So the construction is as follows. So we'll need a new primitive, and this primitive is called a pseudorandom function. And it turns out this can also be constructed using one-way functions, but we will again defer this to a future lecture. So how does the construction work? So what is the definition? The definition is as follows. So consider a function f, okay, which takes two strings, potentially of arbitrary lengths, and produces another string, okay. So suppose that it's an efficient length-preserving keyed function. So keyed function meaning the first input is taken as a key. The second is the function itself. Okay, so then we say f is a pseudorandom function if for all probabilistic polytime distinguishers d, there exists a negligible function such that the following holds. So you're a distinguisher and you have oracle access to the function, the pseudorandom function here. Okay, oracle access, remember, was that you're allowed to ask for evaluations of the function on whichever inputs you so desire, but beyond that you cannot learn anything about the function. Okay, so the only information you have about the function is by asking for evaluations of the function on whichever inputs you have or whichever inputs you choose. So that is what the superscript notation means, or oracle access notation means. So this distinguisher is given access to f sub k, so doesn't see k directly, only gets the function f sub k as an oracle. And on the other hand, or in the other case, the distinguisher gets access to a truly random function f, okay, mapping n bits to n bits. Okay, and here k is chosen uniformly. Okay, okay, and then we can assume that fk also outputs n bit strings when the input is n bit. Okay, so given that these distinguishers have access to these oracles, we require that their outputs should be indistinguishable. Okay, so in particular, and this is without loss of generality, the distinguishers should not be able to output 1 with non-negligible difference in probabilities. So given such an object or a pseudorandom function, so we see why it is pseudorandom, right? Because f is an actual random function, f sub k is a keyed random function, and nonetheless, the distinguisher is not able to distinguish between being given access to an actual random function versus a pseudo-random function. Okay, so how do we use this? So the way we use it to get CPA security is as follows. So suppose f is a pseudo-random function, then the encryption scheme is as follows. You start, so the gen scheme is the same, it just produces a string k or a key k of length. Okay, so the key k is a uniformly random string of length n. The enc algorithm on input k, which is of length n, and a message m, which is also of length n, chooses an r uniformly at random. Okay, so far our encryption schemes were deterministic, right? We saw the one-time pad that was deterministic, and we saw the one based on the pseudo-random generator that was also deterministic. Now it's not going to be deterministic. So the encrypt algorithm samples some randomness itself every time you run it, and it outputs the following ciphertext. So it outputs the randomness r that it sampled, and then it XORs the message m with the pseudo-random function evaluated on little r. Okay, and then the decrypt procedure is the following. So given the key k, right, and a ciphertext which is passed as r, s, the message is, it's easy to see that it'll recover the message, right? You XOR the second part of the ciphertext with the pseudo-random function acting on little r. and there's only little r. So okay, so that is the construction. And observe that every time you run enc, right, you get a different ciphertext, and you're again, it's basically having, you know, exponentially many access to exponentially many pseudo-random generators, right? So you can, every time you use a different r, it's as though you're using a different pseudo-random generator. And then once you know the pseudo-random, like, you know, because fk, you know, the key k is known, so both the sender and the receiver are essentially sharing infinitely many pseudo-random generators, and they use only one. So the probability that they use the same pseudo-random generator twice is very small, because, you know, r is sampled uniformly at random. So you can think of r as indexing which pseudo-random generator to use, and then it essentially acts as a one-time pad where you're using the key only once. Okay, so that's the idea. Yeah, of course the proof is a bit more, you have to be a bit more careful, but that's the key idea. And this gives you a CPA secure scheme. Okay, so assuming that the pseudo-random function is indeed a pseudo-random function, then what you get is an encryption scheme which is secure against chosen plain text attacks.